So that's what Hooke's law is. That's what extension is. That's what spring constant is. What's elastic energy? Well, elastic energy is the energy that is contained within the spring when I've stretched it. So this spring over here on the left has no elastic energy. If I doing it, like it has nothing trapped within it, whereas the one in the middle does. It's been stretched. So if I were to let go of it, if I were to pull it down and let go, then it's going to shoot up, isn't it? It's going to turn itself into kinetic energy. Now, if I pull it back even more and let go, it's going to have even more kinetic energy, right? So it stands to reason, it makes sense that the more I stretch the spring, the more the more energy it has, yeah? The more elastic energy it has. Also, if it took me a lot of energy to stretch the spring because it has a high spring constant, it's very difficult to stretch the spring, then when I let go, imagine if you squashed like a really thick spring, right? Really, really thick, like the kind of spring you might use on car suspension, and you pulled it about 5 centimeters and let go, right? It's going to do a lot of damage, isn't it? Because it's a heavy, even though it's only 5 centimeters, it's a hefty spring. It's contained a lot of energy is contained just within those 5 centimeters. So the spring constant is going to affect the energy too. All right. So the formula for elastic energy, which we're going to just call EE, capital E for energy, little e for elastic, is equal to, it's going to have the spring constant in it. So if I increase the spring constant, I'm going to increase the energy. It's going to have the extension in it. So if I increase the extension, it's going to increase the energy. So the rest of it, for now, we're just going to remember it. It's going to be a half of that multiplied by the extension squared, which it's a bit weird, but it looks a lot like another type of energy, kinetic energy. Yeah, exactly right. So you can at least do that. In fact, it's good that you know that one because they give you this one, but they don't give you that one. So so they'll give you this one and they won't give you that one, but they do look similar, so you can kind of use the one to remind yourself about the other one. So I think it'd be probably worthwhile. Well, first of all, let's just look at how this applies. So if I got a spring and I stretch it, and the extension is 3 centimeters, and the spring constant is going to equal to 5 newtons per meter. Well, let's make it a bit harder actually, because I'll show you how this could be very difficult. Newtons per centimeter. Now, well, the first thing you've got to do here is you've got to turn these centimeters into meters, because when we're getting an energy, the energy is in joules. So we want the units to be in standard units. We can't mess around with like centimeters and stuff like that. We need to change them. So 3 centimeters is, well, if we divide it by 100, then we'd get the meters, because we know there are 100 centimeters in a meter. So 0.03, so 0.03 meters. This one's a bit trickier. Well, it's 5 newtons in every centimeter. So how many newtons would there be in a meter? You're going to multiply it by 100. Because if there's that many in a centimeter, then in 2 centimeters there'd be 10. In 3 centimeters there'd be 15. So in 100 centimeters, it's going to be 500 newtons per meter. Okay. So now we've got our spring constant in newtons per meter. We've got our extension in meters. We can then work out the elastic energy. which is half times 500 times 0.03, and then remember you've got to square it. Now, looking at this, do you think we're expecting a number? What sort of number do you think we'd expect? Are we expecting around about 10 to 100, or maybe less than 1, or more than 1,000? What do you think? So the way that we can think about whether or not it's going to, what sort of size number are we going to expect, is by looking that this is 2 zeros here, and this is 300s, and this is 500s. So these lot will cancel out, but you're going to square this one, aren't you? So you're going to times it again by 0.03. So you're going to expect that you're going to get a number that's going to be a fair bit less than 1, I think. So let's go through that. And also, by the way, we're going to divide it by 2 as well. So we're going to times by half. So half times 500 is 250. And then times by, well, 0.03 squared. Let's look at that. I mean, obviously, we can put the whole thing in the calculator, but I want to sort of go through the stages so we can understand it. So it's 250 times 0.0009. So the 3 squared, obviously, but then it moved. Yeah, anyway, that's what it is. So I times that by 250, and I get 0.225 joules. It's not loads less than 1, but a fair bit less than 1. Okay? Yeah. So one of the things they want you to do for this is to kind of get a feel for numbers and sort of expect. So because they want you to, well, it's a good idea to do it, because as you're doing these questions, you'll notice, the answer that I've got doesn't look right, and you might have missed a decimal point on your calculator at some point, because you're doing this really, really fast, aren't you, in exams? So it's good to get a feel for numbers for that reason.